Okay, so now that I state such a result, one may wonder how do we prove that kind of things. In fact, in the papers that are quoted there, the result is proof only for a finite state space. And in fact, they prove that by extending, let's say, what we know for Lévy processes, okay? Because there is a finite number of changes of dynamics that appear in every exponential interval of time, like in this drawing. Okay, so by doing that, it's more or less easy using some matricial analysis to get these kind of things. Okay, but in a more general setting, we need other tools. Okay, but there are some tools that are again available that were developed by Maisonneuve, okay, which is the theory of exit systems. And to use that theory of exit systems, we need to observe that if we study psi infimum t, the infimum of psi s for s is more equal than t, infimum 0, and psi of power t, the supremum t psi supremum 0, these two for t positive, then it is known that jt and then psi minus psi down arrow t for t positive and jt and psi of arrow t minus psi t for t positive are Markov processes. Actually, strong Markov. Okay? And the proof is essentially the same as the one we know for Lévy processes. It's I will say, an easy exercise. Okay? Or not a very difficult exercise. So once we know that, okay, we can study the excursions from the state space J, or for J, times 0 for these processes. Okay. And here, what I have in this drawing, that's why I kept it, is one excursion from the infimum okay, and I can draw the other ones. Okay. So these excursions, as I said before, they will depend on the color we are starting, in which dynamics we are. Okay? But we also need to keep track of the colors we change inside the excursion. Okay? That's why we need to take care of both processes, J and the process reflected. Okay? But these two processes are Markov, okay? And we can study these excursions from this, and then we can use the Maisonneuve theory of exit systems to study the excursions of these guys. Okay? So for that, we need to consider the zero set, so the set of points where this difference is equal to 0. We do the same for the supremum, okay? We do the same for this guy here, okay? And then, well, we assume some regularity on the ways we hit 0. Okay. And then, we can use this theory of Maisonneuve that was later extended by Caspi and Schindler that tell us that there is an additive functional L, that is the local time. This is telling us how much time my process is spending on zero, okay, like in here. So I reach a new infimum. I spend some time in zero, okay. So this tells me how much time I spend in zero. And it tells me also that there is an excursion measure. So I measure a kernel now that describes the excursions, okay? But it will depend on the colors. Okay? And for that processes, we don't have anymore the Poisson point property of excursions. We may have a Cox process, so a process that depends on another environment, but we have this compensation formula, okay, that tell us that if we make a sum over the left extreme of excursions, okay, and we see this is something that describes the path of the process up to the time g, okay. So this time here, this times is a g, this one is another g, this one is another g, and so on, okay? There are many times where I start an excursion, okay? So yeah, if I add over all those g's, I observe the path up to that time g, and I observe the excursion starting at g, okay? What I get is the expected value of the integral with respect to the local time. So this is telling me where to start the excursion. So L is telling me where do we start the excursions, okay? And then there is a measure that describes the excursions. Well, this P star is for the whole path after the excursion, but we have, if we just observe the excursion, we use the notation N underline J. Okay, so this is for the excursions from the infimum, starting in color J. Okay, we can do the same for the supremum. Okay. Okay. Under this excursion measure, we have that the process, that the path is the same, that the law of this path is the same as that of the process psi tilde when it goes below 0. Okay, so if you observe what is happening inside one excursion, okay, you need to know how to move, how to start the excursion. That is the entrance law. Okay, and then once you are inside the excursion, you will just the particle will just behave as the law of the original process killed when it passes below 0, so that I reach a new infimum. Okay? Well, if we have these kind of formulas, then we can do, in fact, all the calculations we need in the fluctuation theory of Lévy processes. That's the most important thing to keep. Okay? So that there is a formula that is coming from the theory of exit systems that allow me to do most of the calculations that we are able to do for Lévy processes. For instance, to prove the Wiener-Hoff factorization and many others. Okay. 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 Where should I write that? Yeah, that's okay. Okay. And there are some objects that are very important related to these excursions. Is again the downward ladder process. Okay, so take the local time. So the time, the function that tells us how much time you spend in the infimum. Okay, take the inverse and observe the position of the infimum at that time on its own, and the color of the process at that time. Okay? So now this triple is again a Markov additive process. Okay? But the paths of these guys are non-decreasing. Okay? This is just describing, okay, the infimum, as they said yesterday. Okay, this is h hat minus h hat. Okay, the times where I reach a new infimum. Okay, this is the image of tau. Okay, and then the colors. The colors where I reach a new infimum. Okay, that is again a Markov additive process. Okay, and there is a formula for the Laplace transform of this couple that is written in terms of the distortion measure, as it is for the ladder height process of Lévy process. Okay. It's not important that formula at the moment. Okay, but this allows to describe the whole path of the process. That's the most important thing, because we know the infimum, we know where we are reaching new infimums, okay, which colors we are using to reach new infimums, and we know the distortion measure. So in principle, with those 4 elements, we can describe the whole path of the process and do most of the calculations we need. Okay, so the question is whether we can describe these guys precisely. This Laplace transform gives us a way to do it, okay? And there is another way to do, which is via the potential measures. Okay? And the potential measures are one of the most useful elements in this part. So take this integral on S on the positions we reach in the new the colors where we reach infimum, the times where we reach infimum, and the positions on the infimum. Okay. So this is telling us how much time we are spending in those positions in total. Okay, the expected value of the time we spent in those positions. Okay. Well, this characterizes the downward ladder height process. A similar object characterizes the upward ladder height process. Okay. But this formula, this potential appears in many areas, in many formulas, like for instance this one. Okay. So what is this formula telling us? So if we want to know the position of the process, the Lévy process, at time t, not the Markov additive process at time t, when we are inside excursion, okay, what do we need to do? We need to know, so imagine, again, this is my drawing, so now there are no exponentials, okay? So I have the process at time t. I have time t, I am in some position, psi t, and I have a color jt, okay? I'm inside excursion. Okay. So one way to describe this position is, if I know the excursion measure, is know the law of the excursion, and then how I reach that excursion. So what I need to do is go in this direction, okay, and then start the excursion, okay, that is long enough to be there at time t. Okay, so this time here is gt, is the supremum of the s smaller than t, where psi s is equal to psi down arrow s. Yeah, it's the last excursion. Okay, and this excursion is long enough. Okay. If this is equal to S, that S has to be smaller than t, and has to be also such that t minus s, the remaining time, is smaller than the lifetime of the excursion. Okay? And there's just one excursion that does that. There are no infinitely many. Although there are infinitely many excursions before, there is only one that does this. It's a final excursion. Okay? And this is what is said here. So you have this is the excursion. Okay? So I move into a position that is given by x minus c. Okay? So this is the position x now. So I go negative to some position c. Okay? And then I move according to an excursion. This is the excursion process. Now under this measure. Okay? And I move to some position c. And that position c, okay, I do it according to the infimum, isn't it? So I reach this position according to the kernel u minus. And this is telling me also in which color I should start the excursion. Yeah? Okay. For instance, I can also add another restriction here. I can add the restriction that I have not been below 0 before time t. And that will just restrict this measure here, okay, so that the infimum is not bigger than x. Yeah? Okay. So if I start at x, 0 is below, okay, so the infimum should be smaller than x. Okay. Well, so this potential measure is very useful, okay, and this is what we need to describe the law of psi and this excursion measure. Okay. So we need to identify these guys. That's essentially the message. Okay. Yeah, well, the proof of that is just what I said. So we just need to count on the excursions that start before t and that finish after time t minus s. And by the compensation formula or the master formula, we can write that in terms of the local time, and then we make a change of variables so to get the potential. Okay. Well. Okay. There is a similar formula for the case where we are not inside excursion, but we are starting excursion. Okay? When we are starting excursion, we have a similar formula. Okay? Just we need to take a density here in time s. It's just like the creeping, not the creeping, the having a heavy set in a stable, in a Lévy process. Okay. So how, now that we know that this potential measure is so important and the excursion measure is so important, how do we determine that measure? If we want to say something useful, how do we determine that? In particular, if I go back to the questions I raised at the beginning of the lecture, how do I determine that for stable processes, for instance? Can I say something for stable processes of dimension bigger than 1? Where do I find that kind of potentials for stable processes? Okay. This one. Okay. If we use, before I describe how do we get that for the stable, let me just tell you that if we have that formula, this formula that we have here, Okay. We can integrate with respect to exponentials, okay, and prove the Wiener-Hoff factorization using this and the duality. Okay. And the final formula for the Wiener-Hoff factorization looks like this. Okay. So we have that these random variables are independent given this guy. Okay, so the position where we start at the excursion. Okay, and then they are independent, and the laws are given by this quotient of excursion measures. Okay. For yes, it's 0. Yeah, I started at 0. Yeah. But in J, I start at pi. Yeah. I should start in the stationary state, so that when I run this backwards, I see the same thing. Yes, that's important. I cannot do it from a fixed point, unless the process allows me to do it. But in general, I need to start from the stationary state. Yeah, this is using duality. I need to run backwards the process. Okay, so now we have the question I raised before. Okay, so how do we determine these potential measures in general? Okay, and what else can be said once we know that kind of things? Okay. Okay. For stable processes of dimension 1. We can get the upward ladder height process, the upward ladder height potential. Okay, this is just in space, not in time. Okay, and there, remember, when we're in dimension 1, we just have two processes. We have one for the positive side and one for the negative side. Huh? Imagine this is the path of a stable process. Okay. So I take the absolute value of x, okay, and I keep track of the color. So I flip this path upwards. Okay. I have two processes. Now I take the supremum of this guy. Yeah, or I take the infimum of this process. I can take both. Either of them. Okay, so the supremum will be taking different colors according on the new supremums or infimums. Okay, and these two processes of the supremum or infimum can be described precisely via the potential measures. Okay, so the potential measure of this guy that is going upwards is u plus. Okay, and this one is u minus. So the measure that tells us how much time we spend in a position and in colors where we reach infimums or supremums. Yeah? Okay. Because I only have two possible states in J for the supremum, in the potential measure, I have actually a matrix valued measure. Yeah? So this is for starting in color 1 and passing time in the supremum at color 1. Okay, starting in color 1 and passing time in the supremum in color -1, and so on. Yeah. Okay. So here again, we have something that depends on the positivity parameter of the stable process. Okay. But we have also something that depends on the negativity parameter. Look that is different to what happens in the case of where we observe only the upper ladder process of a stable process killed when it passes below 0. Yeah? Because when we observe just the upper ladder height process of a stable process killed when it passes below 0 via the Lamperti transform, we are just observing this white color. Okay? We don't take care of this. Okay? So we don't take care of the negative part of X. So there is no rho hat appearing. Okay? Here, because I'm taking care of also of this, here in this part in red, I'm also having terms appearing in rho hat. Yes? Okay. So we have that kind of formula. And that kind of formula can also be extended for alpha between 1 and 2. Okay. Okay. And to get that kind of formulas, we use these identities. These identities are similar to the ones I described before. Okay? So if I take the last time of an infimum, okay, up to an exponential time, okay, and I just see the color where I am starting the excursion, I have a similar formula to the one I wrote before. I just need to plug exponentials because of this exponential here. Okay, so there is this exponential appearing here. Okay, but in particular, one thing that is important is that if I make Q go to 0, okay, in the case where the process is going to plus infinity, I have a final excursion that will start in some color. Okay? When alpha is in between 0 and 1, a stable process of dimension 1 never hits 0. Okay? So that makes that if X is seen as the Lamperti transform of a Markov additive process A and psi should be going to plus infinity. It cannot accumulate, isn't it? Because we need that the exponential cannot go to 0. Okay? But there is more. We have also that the limit as t goes to infinity of the absolute value of xt is equal to plus infinity in this case. Yeah? So that makes not only that we are not going to 0, that psi is going to plus infinity almost surely. Yeah? Okay. So in this case, there is a final excursion from the infimum. So in this drawing here, okay, we eventually have an excursion of infinite length. Yeah? Okay. If this excursion happens at time g infinity, okay, we will reach some position psi infimum g infimum, psi infimum infinite, okay? And that distance here may happen in either side of x. It may happen on the positive side or the negative side. Remember, I'm thinking on the two paths, on the path of psi and j and on the path of x, okay? So this bit that is here is the part that's coming from x, okay? So this position that we have here is what we call the point of closest reach of 0 for x, okay? Well, the exponential of psi. But this is something, again, that is described by an infimum of the process. So it should be described in terms of the potential measure of the downward ladder height process. Yeah? Okay. That is why we need these kind of formulas. Yeah? So here I'm starting at x. I am saying that I'm not going below 0. Okay, so the infimum should not be below level x. Okay, so the infimum cannot be. So the downward ladder height process cannot be too big. The upward ladder height process should be smaller than x. Okay. So what I'm saying here is that the distance from here to this point here, this distance is smaller than x. Okay? Okay. And then I need to find in which side, in which color I'm starting the excursion. Yeah? Okay. This is what I'm doing here. Okay? And in particular, we have this kind of identities, that this quantity here that I am looking for, I will be looking for this quantity because it's a vector that I will need to find. It should solve this equation. Okay. Okay. And having a point of closest reach of this or that size, okay, is related to the stable not hitting this interval. Okay, that is what is being said. Okay, so a stable process starting from x and not hitting the interval minus 1, 1, okay, has explicit formula, and that's something that was proved by Blumenthal-Getturen array. Okay, and later extended by Cipriano, Watson, Pardo. Okay, so they obtained this formula using again the Lévy process that is associated to this stable process. Okay. Yes. Okay. So once we have this kind of formula, then we can read from this formula the point of closest reach, and then go back and find the downward ladder height potential. Okay? And that once we know how to do that, then we find this one. Okay? Which is the one that we are looking for in the matrix. Okay? And we can do something similar for the supremum and so on. Okay? So that kind of computations lead us to these kind of formulas. Some explicit formulas. So these are, it's like, it's identifying explicitly the downward ladder height process and the upward ladder height process of a Markov additive process. Okay? And that is a kind of game, okay? We can play with the stable. So when we have an identity for the stables, how we transfer that into an identity for the Markov additive process that is behind, either for the upward ladder or downward ladder process, or for the whole process, okay? And vice versa. Once we have something for the Markov additive process, how do we translate that into a property for the stable? Okay. Are there any questions up to there? No? Okay. Yeah. Okay. Now I will remove this. Can be, well. Can we now remove this? I think I'm not going to use it anymore now. Okay, what happens in a bigger dimension? In a bigger dimension, for the moment, we just know how to work in the rotational invariant case. I mean, the tools are there to work in the... Okay, the tools are there to work in a non-rotational invariant case. Okay, but the problem is that the identities that we use to read something from a stable or translate something from a stable into something for the Markov additive process are not known for rotational invariant processes, not non-rotational invariant stable processes. Okay. Well, in dimension d bigger than 1, x rotationally invariant, one can prove that the norm of xg infinity, which is the infimum of s positive of the norm of xs, okay? Because we're in dimension bigger than 2, the process x will not hit 0. Okay, so the infimum of the radius will be strictly positive. Okay? In fact, the process will go to plus infinity. Okay, it will enjoy, it has a lot of space. Okay. Then we have that the point of closest reach has a law that is given by starting from a point x, xg infinity being in dy is equal to pi to the minus d divided by 2, gamma d divided by 2, gamma d minus alpha divided by 2, gamma alpha divided by 2, norm of x to the square minus norm of y to the square, alpha divided by 2, x minus y to the d, norm of y to the alpha, dy, and this for y whose norm is smaller than x. Okay. This is something that is new. Okay, it was not known before this paper that we finished with Andreas and Pite some months ago. Okay. So Cipriano, Chatit Canicul, and myself in 2018. We were able to prove that using these techniques of Markov additive processes, okay, and using a theorem by Blumenthal, Guitur, and Ray, that is from the 60s, okay, that tell us if we have tau r minus the first time where the norm of xt is bigger than r, okay, then the probability starting from x and x tau r minus, yes, is in the y is equal to a constant pi d divided by 2 plus 1 minus gamma d divided by 2, then c of pi alpha divided by 2, and then r squared minus norm of x to the square alpha divided by 2, and then norm of r squared minus norm of y. Okay. And then also there is an expression for the probability starting from x that we never go below, we never hit a ball of radius r, tau r plus and this is gamma d divided by 2, gamma d minus alpha divided by 2, gamma alpha divided by 2, and then the integral from 0 to norm of x squared divided by r squared minus 1, u plus 1 to the minus d divided by 2, u to the alpha divided by 2 minus 1 du. And using these formulas, but in a more involved way than in the one-dimensional case, we are able to get these kind of formulas. Okay? But remember again, this guy is given in terms of the potential of the downward ladder height process. Okay? So in fact, in the proof of this result, we did the opposite. I mean, in the one-dimensional case, we were able to find this from this identity, okay, from these two identities. We are able to get this, and from this, we find the downward ladder height potential measure. Okay? In the one-dimensional case, we are able to read from here u minus. Yeah? In the bigger dimensional case, we cannot do the same. Okay? So we use a different technique. We use again these kind of things. We obtain u minus, and once we got u minus, we got this one in particular. Okay? And the reason for that, that is very subtle, is that from here, especially from this, what we need in the one-dimensional case, is this off? No. What we need in the one-dimensional case is this probability here, this distribution. But in this distribution, we can only read something about the radius, because this is never hitting a ball of radius r. Okay? In the one-dimensional case, that is okay, because it's just an interval. Okay? And the interval, we can put it wherever we want, so we can play with the signs without a problem. Okay? In the d-dimensional case, we cannot, because this is not giving us information on the angle. Okay? So we need to play a more subtle game, okay, to read from these two guys something on the angle. Okay? Remember here, we have something on the angle, starting point, and the radius. Okay? The infimum of the radius. Okay? So, yeah, the game was a bit more involved, but once we were able to do that, we got U minus, we got these kind of things, and then we were able to get more stuff, as for instance, more information about how we hit a sphere. And that, well, is something else that I described 2 weeks ago in the lectures in Tokyo. But so imagine you have a sphere of radius r. Okay, so you have the path of the process. It moves around. Okay, and eventually it hits the ball. Tau r plus. Okay. That this is given by this probability here. Okay, but now knowing U minus, we can say more. We can say which was the time, where was the position that I was closest to the ball before hitting the ball. Okay, so we have x infimum, so g tau r, okay, which is the point of closest reach of the ball, okay, before entering the ball, okay, and then also this position here, because once we have U minus, we know that this position that is here is given by U minus. We have to reach an infimum in the radius before entering the ball, okay? And then we have to move inside the excursion, and moving inside the excursion is moving in this direction, and this is given by 1 U plus, but by rotational invariance, this U plus will have the same law as U minus, will be the same measure. And then we know the distribution of the jump. Okay? So by determining this U minus, we got at least 2 extra informations: the position of the low of the point of closest reach, okay, and the point of closest reach of the sphere before hitting the sphere. But we can get many other informations. Okay. I don't know if I want to do the proof of that because the argument is more involved, so it becomes very technical. Yeah, I will tell you now just the starting point, the starting argument. So in the proof of this expression there, we consider function delta rfx, which is the expected value starting from x, 1 over delta of f of the argument of x of g infinity, which is the guy we are looking for, and then the radius of x of g infinity. And we require this to be in r minus delta r. Okay? And we're going to take the limit as delta goes to 0. Okay? So to get the marginal density of this guy and the distribution of this one, okay? Of the argument. Okay? And in order to do that, well, we need for the infimum of the radius, or the point of closest reach of to 0, we need to at least enter once into the passing below the level r in the radius. Okay? So this is equal to 1 over delta, the integral from y in r minus delta r, okay, and then the px x tau r plus, so entering into the ball of radius r is in the y, and then tau r plus to be finite. This guy that we have here is coming from one identity like this one, given by Blumenthal-Getturen array. Okay, so this guy, we know it explicitly. And then, by the Markov property, once we are in the position y, we find this position of the last infimum. So we have f of the argument of x g infinity, and then norm of x g infinity is in r minus delta r. Okay? This one here is u minus dc starting from y of f of the argument of c, then indicator norm of c is in between norm of y, norm of r minus delta. Okay. And this is known by the Blumenthal-Getturen array formula explicitly. It's that formula that I have on the right. I will not write it again because I don't have enough space. Okay. And then when we take r minus delta, delta going to 0, this term is going to r. Okay, so this will be essentially r. Okay, but this guy also is going to r. Okay, so eventually this guy here, when we make delta go to 0, this will go to f of the argument of y. Okay, and then I will get the fy going inside, okay, and I will have only something that is the integral of this on r minus delta r, so f of y, okay, So by making delta very small, I make this just a starting point. And I get this term here, so I get rid of this f inside. And that is just something that is now depending on the radius. Okay? And this term that I have just depending on the radius is given by this term here, essentially. Okay? And at that point, I'm making x very close to r. Okay? Because I know I have this explicitly, okay? I know how to control that. Okay? So by that formula that I have here, I get a way to control this guy, and I put it inside the integral, okay? And then I get the limit of this. Okay? That is really, really kind of magic. Okay? So by making this delta very small, I put f outside. Okay? I use estimates for this, and I'm able to get this limit here. Okay? Well, yeah, I don't want to give more details because it becomes quite technical. And it has been already quite technical, and it's Friday afternoon. I think it's a good moment to finish. I will finish a little bit earlier. Yesterday I took 10 minutes more, so I'm giving it back to you. But I would like to finish saying that there are a lot of things that can be done for these self-similar processes in dimension bigger than 1, okay, and objects related to that. For instance, everything what is related to exponential functionals of Markov additive processes, there is very little that is known. But because we know the theory of Lévy processes, and we know that Markov additive processes have a parallel theory to that of Lévy processes, one can expect that there are similar results holding. Okay? So there is a lot of research to be done in that area, like trying to establish the parallel of the results known for positive self-similar, okay, or for exponential functionals of Lévy processes into similar results for self-similar processes of bigger dimension or exponential functionals of Markov additive processes. And that is more than a curiosity. One of the reasons is that, for instance, for a stable process, we just know things for rotational invariant. So if we get a good machinery, then we can develop more theory for non-rotational invariant stable processes. Okay? And these exponential functionals of Markov additive processes, they are appearing in many areas of probability, of applied probability. So that's it, and I thank you very much for your attention. Thank you, Kuyi, for the invitation. Thank you to the University of Kyoto for having me here. It has been a very nice experience and very pleasant to give these lectures. Thank you.